Let's see, everybody. I'll minimize myself. I don't need to see myself. I need to see you guys. I need to see you guys. Hello world, it's Siraj. I am hyped for this live session. Yo, class is in session, everybody. We are about to do some math this live session, so I'm super excited. But first of all, let me take some roll call, all right? So let's see, Colin, Brandon, Neil, David, Bikash, Sebastian, Raj, Spencer, Naresh, Nico, Clement. Hi guys, Michael, Benjamin. All right, so that was roll call. Welcome to this live session for the deep learning, intro to deep learning course. Okay, this is going to be so awesome because I have been waiting to do some math. And guess what, guys? Guess what? I bought this pad to write some math on. Okay, and I've never used this before in a live stream, so I'm super excited for this. I'm going to show you guys the math behind linear regression. By the end of this video, you guys are going to know, like the back of your hand, how to do linear regression. That includes gradient descent. And guess what? We use gradient descent all over the place in machine learning. Don't worry if you don't know what that is. I'm going to show it to you, okay? So we're going to deep dive into this. So we're going to start off with a 5-minute Q&A, like always. And I think we've got some Udacity peeps in the house as well. Dhruv, Nico, and Matt, who's the other instructor for the course. So in Udacity, guys, if you're I think you're here, shout out, like say something so people know who you are. And so I'm gonna do my 5-minute Q&A, like always, and I'm gonna answer all the questions related to me and my everything. But if you have any like Udacity specific questions, they will answer those, okay? So let's start off with a 5-minute Q&A, and then we're gonna get right into the code and math, okay? Do I have to know about partial derivatives? We are gonna do a partial derivative, but I'll show you how that works. I had to cut off PewDiePie to catch this. Wow, I'm honored. I'm honored. Hey, baby girl, let me see that regression. All right, so that's not a question, guys. Let's get some real questions in there. Some quality questions. All right. Would you want to check out my Vive AI assistant demo? Sure, yes. Post a GitHub link in the comments of one of my videos. I read all my comments. I answer all my comments. See, I'm not fake. You know what I'm saying? I answer all my comments. I'm here for you guys. Have I enrolled in? Is calculus required for linear regression? Yes. A little bit of calculus, but I'm going to go through that. Don't be afraid by the word calculus. This is actually very intuitive. Can you mention some details about the upcoming as well? Looking to predict genre from. All right. What basic maths will be needed? You'll need to know basic algebra, okay? And then we're gonna learn the calculus necessary to do this in this video, okay? Are GANs the future? Yes. I mean, the idea between generative models in general are really exciting because you can generate things that don't exist. And that has a lot of potential for art and culture. GANs can change culture, right? We can generate music, we can generate art, we can generate paintings in ways that humans couldn't. Best book to understand math behind ML, Machine Learning, a Probabilistic Approach. That's a pretty good one. Just math today or coding too? Both, mostly coding. Linear regression versus other classifiers like SGDC. Linear regression is definitely easier. What is no free lunch? It's a theorem, the no free lunch theorem. At a very high level, it's like, well, you can't make assumptions. You can't make assumptions whenever you are doing anything related to proving something. Just when will you do NLP? Yo, I'm gonna do so much NLP in this course. I can't wait for NLP. It's coming up. Will you cover GANs? I kind of want to just do GANs right now. You know what I mean? Like, I'm super excited for GANs. I will do GANs. I will give an intuition why to do gradient descent over yes, I will explain that. Linear algebra is the way to go, yes. What's the difference between scikit-learn and tf-learn? Scikit-learn and tf-learn, great question. So tf-learn is a high-level wrapper on top of TensorFlow. It's very similar looking to scikit-learn, but scikit-learn specifically is, it does, so tf-learn only focuses on deep neural networks. Scikit-learn uses support vector machines and all sorts of other machine learning models, whereas tf-learn is the same kind of, it has the same brevity, but it focuses only on deep neural networks. Do you prefer Weka? No. No. Weka's no. When will you start working on Anaconda? I mean, I'll most likely start using Docker to containerize things. All right, wrap for 50K subs. Okay, let me wrap for 50K subs. And this time I'm going to play an instrumental. I'm not just gonna rap without an instrumental, you know what I mean? So let me just search rap, hip hop, instrumental on YouTube, whatever starts playing. Someone say a keyword and then we're gonna get started. Triumph hip hop instrumental, what is this? All right, let's go, play it. All right, let me just unplug my mic so you guys can see this. Where's the music? Where's the music at? Someone say something, you know what I'm saying? 50K subs. I got 50K subs, man. My mind is so fresh. I'm looking at this coffee, man. It looks like the best. I got caffeine on my mind. It takes me so high into the sky. I got a USB port, my oh my. I'm gonna be writing math today like it's all mine. Online, I see it, man. It's all fine. As I write these equations online, I see it coming back like linear regression, gradient. My. Okay, so that was it. Okay, so that was it for the wrap. Okay, so now we're gonna get started with the code, okay? So let's go ahead and do this. I'm gonna start screen sharing and then we're going to get started. All right, here we go. Here we go, Google Hangouts. All right, and what does Hangouts want to do? Hangouts wants to screen share. Hangouts wants to screen share. Your entire screen share. All right, so I'll minimize this and minimize, and then I'll move this out of the way so I can see what you guys are doing. Okay, and we're gonna code this baby, okay? I'm in the corner here. Let me make sure that what you guys are seeing is what I want you to see. Yes, what you guys are seeing is exactly what I want you to see. Perfect. All right. Okay, so here we go. Here's what we're gonna do, guys. Let me make this big. Test. This is big enough, right? Okay. So in this lesson, we're going to do linear regression, okay? And what is linear regression right now, okay? So linear regression in this case, and let me make sure everything's working. Everybody's here, live chat's working, live video's not working. Okay, so here's how it goes. So we're going to do this, okay? So this is gonna be called linear regression. This is linear regression, and let me just show you guys. The best way to explain it is to show it to you visually. So I'll show it to you visually, what exactly we're going to be doing. And to show you visually, I will give you a link to this, and I will just show it right here. This is what's happening. So we have a set of points, and these points are these points are the test scores of students and the amount of hours studied. Okay, so this is what it looks like. So this right on the right, this graph here, these set of points the x values are the amount of hours they studied, and the y values are the test scores they got. Okay, and intuitively to us, there must be some kind of correlation between these two values. But we want to prove this programmatically. We want to prove, mathematically. We want to prove that there is a relationship. And how do we prove that there is a relationship? We draw a line of best fit. So how do we know what that line of best fit is, what that linear regression is? Well, we don't know. We don't know. We have to find that. And the way we're going to find the line of best fit is using gradient descent. And that process, that training process, looks like this. We're going to draw a random line, compute the error for that line, and I'll talk about how we're going to compute that error. And that error value is going to say, how well fit is this line to the data? And then based on that error, it's going to act as a compass. It's going to tell us, well, how best should you redraw the line to be closer to the line of best fit? And we'll keep doing that. So it'll be like draw a line, compute error. Draw a line, compute error. Draw a line, compute error. Until eventually, the line that we draw is the optimal line that we should draw, okay? So that's at a very high level. But now I'm going to go into the code, and we're going to talk about this in detail. All right, so let's go ahead and get started. So to start off, I'm going to write my main function. Okay, so let me move all this stuff out of the way so I'll get right into the code. All right, I'll get right into the code for this. And guys, also, if people have questions and I'm not able to answer them because I'm busy doing something, please help me answer questions. I very much appreciate it. Okay? So let me just start off by writing the main function. Well, what does the main function do? Well, that's where the meat of the code goes, right? Okay, so in the main function, we'll write the run function, which is where we're gonna store all of our logic, okay? So let's write out the run function. So the run function is a chance for us to show what we're doing at a high level. So step one is collect our data, right? Always in machine learning, we want to collect our data. So we'll get our data points. And what we're gonna do, how are we gonna collect our data, right? Well, to collect our data, we have to import the one library that we're using. I know, guys, we're using a single library. And that library is NumPy, all right? And we're gonna use this little symbol that means we don't have to continually say NumPy whenever we call its method or its functions. Okay, so what is the function we're gonna use from NumPy? So the function we're gonna use from NumPy, name, thank you, name, good call. So the function we're gonna use from NumPy is gen from text. And what this is gonna do is it's going to get the data points from our data file. And let me show you guys the data file as well. But basically we're gonna separate it by the commas, okay? And we're gonna get those points. So what does this data look like? Well, let me pull up terminal and show you guys exactly what this data looks like. So it looks like data.cxv. Okay, so let me zoom in on this. Hold on. Zoom way more, 200%. So these are just the hours studied on the left side, and then the test scores for a bunch of students for an intro to computer science class. Okay, the hours studied and the test scores they got. Okay, so that's what we're gonna pull. That's our data set. That's what we're gonna pull into our points variable. So it's points is gonna contain a bunch of x, y value pairs, where x is the amount of hours studied and y is the test score. Okay, and it's separated by the comma. Okay, so that's step one. We've done that, and get from text is essentially running two main loops. The first loop converts each line of the file into a sequence of strings, and the second one is converting each string into the appropriate data type. Okay, so that's step one. Now step two is to define our hyperparameters. Okay, in machine learning, we have what are called hyperparameters. These are tuning knobs for our model. They are basically the parameters that define, how our model is analyzing certain data, how fast it's fitting to the data, what operations it's performing on the data. There's a whole bunch of hyperparameters. Thank you for the feedback. There's a whole bunch of hyperparameters, and what we're going to use is the learning rate. Now, the learning rate is used a lot in machine learning, and it basically defines how fast should our model converge. And converge is a word for convergence. Convergence means when you get the optimal result, the optimal model, like the line of best fit in our case. That's convergence. So how fast should we converge? Well, you might be thinking, well, shouldn't the learning rate just be like 1,000,000 if you wanted to convert super fast? Well, no, like all hyperparameters, it's a balance. Okay, so if the learning rate is too small, we're gonna get slow convergence. But if it's too big, then our error function might not decrease, okay? So it might not converge. So that's our first hyperparameter. Our next hyperparameter is going to be the initial value for B and the initial value for M. And what is B and M? Well, what we're going to do is we're going to calculate the slope, right? So this looks like y equals mx plus b. And so this is why I said we only need to know basic algebra. This is the formula. This is the slope formula. Okay, all lines follow this formula where so m is the slope, b is the y-intercept, x and y are the points, okay? So that's the line, okay? So this is our initial b value, our initial slope, and our initial y-intercept. They're gonna start off as 0, okay? So, and then the last hyperparameter is going to be the number of iterations. How much do we wanna train this model? Well, we have a very, very small data set. There's only 100 points, okay? And for that, we're not gonna need to iterate 1,000,000 times or 100,000 times. We're just gonna iterate 1,000 times, okay? So that's our hyperparameters. And now step 3 is going to be to train our model. train our model. Okay, so the first step is going to be to show the starting gradient descent. Okay, at b equals, what is the starting gradient descent? It's going to be 0, right? And then m is going to be the starting point. It's going to, for that, we'll say 1. And this is just for us to see the difference here, okay? Okay, dot format, initial b, initial m. And so, okay, so what's happening here? Compute error for line given points. So let me just write this out and I'll explain. Initial b, initial m, and then the points. Okay, so what's happening here? Let's go over what I just wrote here. So in this line, we're going to show the starting b value, the starting m value. So what is our starting y-intercept, what is our starting slope, and what is our starting error? And I'm going to show you how we're going to calculate that error. And to get that error, given our b, given our b and m values, we have this function here called compute error for line at given points. It's going to take the b, m, and the points, and it's going to compute the error for that, and it's going to output that. So that's going to be our starting point, okay? And then now we're going to actually perform our gradient descent, and it's going to give us the optimal slope b and the optimal slope. Sorry, it's going to give us the optimal slope and the optimal y-intercept. So for gradient descent, we're going to call this method the gradient descent runner. So given points, given an initial b value and initial an initial m value, given our learning rate, so this is where we're going to use all those hyperparameters, right? Because this is where we're training our model. So the number of iterations, those are all the things we need for this. Okay, and we're going to define these functions in a second. Okay, we're gonna go deep dive and define these functions. Okay, so then after we fit our model, well, now we can just print it out, right? So let me just copy and paste this. So now this is not our starting point. This is now our ending gradient, ending point. So say it's our ending point where b is this, b is 2, m is 2, and then error is 3. And these numbers just define what we're going to see at the end. For the number of iterations for b, and then for m, and then for computing the error for line at given points, given b, that the final b value, the final m value, and then our points. Okay, so that is high level what's happening here. So all I did was I just printed out the initial b and m value, which is nothing, and then the error, and then I computed the gradient descent, and then I print out the final values. So I'm about to do this now. Okay, so we haven't actually done it. Now we're going to do it. So the first thing I want to talk about is how we're going to compute that error. Okay, so let's write out that first function. What was that first function called? It was called compute error for line at given points. Okay. Okay, so, and the data set, I'm going to provide that as well. But let's go ahead and write out this method. Okay, so this is the first step. We're going to write out this method, compute error for line at given points. Okay, I'm so excited to show you guys this because I get to use my math pad for a second. Okay, so let me write this out. Okay, hold on. Okay, here we go. Okay, so okay, let me write this out. Okay, so we've got a line here. Oh man, what a great line that is. Okay, so this is our plot, okay? And so we've got a bunch of data points here. We've got a bunch of data points, right? It's all over the place. And what we're gonna do is we are going to draw a random line through that data, okay? We don't know the line of best fit, so we're gonna draw a random line through the data. And then we're gonna compute the error of that line. And so that error is gonna tell us how good our line is, okay? And so how do we know how good our line is? Well, what we're gonna do is we're going to, for every single y value on that line, we are going to calculate the distance from each point from our data to the line, okay? So all of these distances, distance 1, distance 2, distance 3, distance 4, distance 5, distance 6, and then we probably have more data points down here. these distances, the distance to this line. And so we're going to take all those distances and we're going to sum them. And so let me show you the equation for that, okay? So rather than actually writing out this equation, like really, sloppily, I'm going to show it to you using this, okay? So this is the equation. So let me explain what this is. So we got all those distances, right? We got all those distances. We're going to sum those distances together and then get the average of that. But guess what? We're not just going to sum those values alone. We're going to square those values. And why are we squaring those values? Because we're squaring those values because we want it, first of all, to be positive. And it doesn't really matter what the actual value is. It's more about the magnitude of those values, right? And we want to minimize that magnitude over time. So this is the equation for that. Okay, so let me explain what the hell this is, okay? So we are computing the error. We're computing the error of our line given m and b. So given m and b, we're going to compute the error of our line. M is our slope and b is our y-intercept. So this E-looking thing is called sigma notation. It's giving you guys a little refresher here. This E thing, we're going to see it a lot in machine learning. It's called sigma notation, and basically it's a way of calculating the sum of a set of values. All right, so the sum of a set of values. So which is what we're doing. We're calculating the sum of a set of points. So the starting point is where I equals 1, and the ending point, and n means for every point. Okay, so for every point, we want to calculate the difference in y values, right? So it's y minus mx plus b. And why do we say mx plus b? Because in the slope equation, y equals mx plus b, right? So it's y minus mx plus b, which essentially boils down to just y. So it's y minus y squared. And and then we're doing that for every single point. And so we're going to add all of those points together. Okay, and then get the average. And so that's why it's 1 over n, because we're going to get the average of that. And that value is the error. Okay, so at a high level, that is what that is. So now let's programmatically write this out. Okay, so we're going to start off by initializing the error. Initialize it at 0. Okay, so our total error at the start is just going to be 0. There's not anything we don't have an error yet. Okay, so then for every point for every point, so for I in range of starting at 0 and then going for the length of the points, right? So all of our data points. So for every data point that we have, we're going to say, let's get the x value. So, right, so let's get that x value. So x equals points I 0. And then we're going to get that y value, right? So then get the y value, right? So I'm just basically programmatically showing what I just talked about mathematically, right? So we've got the x value, we've got the y value, and we want to compute that distance, right? We're going to do this every single time. Okay, so then get the difference, square it, and add it to the total. Okay, so here's the actual equation, right? So we're gonna be plus equals because it's a summation, and we're going to programmatically show what I just talked about right here, right? Y minus mx plus b squared. Okay, and we're gonna get the sum of that. So y minus m times x plus b squared. Okay. And we're going to do that for every point. So this whole iteration loop right here is that equation, okay? Minus the average part. So that's going to give us the total value. The last part is to average it. So we'll say total error divided by float the length of the point, because we want it to be a float value. And that is the equation. That is the equation right there. Okay, so and then get the average. Get the average. So this 10-line function just described what I talked about right here in this math equation, okay? We summed all the distances between all those points, as I showed right here. We summed them all up, we squared them, and then we got the average. And that is our error, okay? And so and we're calculating that because we want a way for us a measure of us, something to minimize over time, right? We something to minimize every time we redraw our line. We want to minimize this error because this error basically is a signal. It's a compass for us. It's telling us this is how bad your line is. You need to get better. You need to make me smaller. I'm really big right now. Make me smaller. And that's what gradient descent does. That's what gradient descent does. And I'm going to talk to you. I'm going to explain how gradient descent works in a second. But that's that first function, right? So what was the second function we wrote? It was called gradient descent runner. So this is our actual our gradient descent function. Okay, so let's write this out. Okay, this is our second of 3 methods. Before we're done. Okay, so gradient descent runner. So given a set of points, given a starting value for B, given a starting value for M, given our learning rate, and given our number of iterations. We're going to use all of these things to calculate gradient descent. We're going to use every single thing, okay? Okay, so let's get that starting B and M value, okay? So the starting value for B, we're going to set it to B, and the starting value for M, we're going to set it to M, okay? Simple enough. And now we're going to perform gradient descent. What is gradient descent? I cannot wait to explain gradient descent, guys. I found a perfect analogy for gradient descent. I'm really excited. Okay, so before I explain that, let's just perform the iterations because the actual math is going in this third and last function that I'm about to write. So for every single iteration that we define, we're going to perform what's called gradient descent. So we're going to update B and M with the new, more accurate B and M by performing this gradient step. Okay. So B and M we're going to return B and M by performing this gradient step, which I'm going to explain. This is where the math is happening. Given our current B and our current M, given the array of points that we have, and then finally given the learning rate, we're going to calculate that final value of B and M. And guess what? Once this gradient descent is done, we're going to return that optimal B and M, right? And so that's what we talked about at this bottom part, right? It returned that optimal B and M value after performing gradient descent, and we then printed it out because that optimal B and M value gave us the line of best fit. When we plugged them into the y equals mx plus b formula, it gave us the line of best fit. So now we're going to write out the gradient step, okay? And this is gradient mother effing descent, okay? So this is how it's going to go down, okay? All right, here's how it's going to go down. Step gradient. So I'm just going to say it's time for the magic. The magic, the greatest, okay? So that's how excited I am. I just wrote the greatest twice. Okay, so so given our current B and M values, points, and the learning rate, and this actually isn't going to help with learning, so I'll delete that. So given our learning rate, okay, let's perform gradient descent. So, okay, what is gradient descent? Okay, so let me show you guys this. So, okay, how best do I describe this? So we have, let me just show you this image. This is going to help a lot. Okay, so this is a graph, okay? So let's just look at the graph on the, I mean, it's the same graph. It's looking at it from 2 different angles. It's the same graph, okay? So let's look at the one on the left, just to pick one. It's the same graph though. We have a bunch of y values, a bunch of b values and a bunch of m values, and then we have that error, right? That error that I just talked about, right? So the 2D graph would be given every single y-intercept we could have, given every single m value we could have. What is the error? Okay, so for every y-intercept and slope pair, what is the error? And so what we'll find, this is a 3-dimensional graph. This is a 3-dimensional graph because the error value, it's kind of like it starts off high, and then as you approach what's called the local minima, in our case, the local minima, which is the small that point at the very bottom, that is where we're trying to get to. Okay, so given a set of y-intercepts and given a set of slopes, possible y-intercepts and possible slopes, we want to compute the error for those 2 things. And if we were to graph that, if we were to graph the relationship between these 3 things, it would look like this. Now, it tends to always look very similar to this. In more complex cases, we have like many minima. We have many little values. But what we're trying to do is get that point where the error is smallest. And so how do we get that point where the error is smallest? Well, we're going to perform what's called gradient descent to get that smallest point, that valley, that smallest point. And a great analogy for this, is a bowl. So let me just search bowl, okay? Okay, it's kind of like a bowl. It's like we drop a ball into a bowl, and we want to find that point where the ball stops, that end point, the lowest point. That B and M value is our optimal line of best fit value, okay? And the way we're gonna get that is gradient descent. And we're gonna descend, right? We're descending down the bowl using the gradient, and gradient is another word for slope. We're gonna descend down that bowl until we get, through iteration, that lowest point. And gradient descent is used everywhere in machine learning, okay? It is like the optimization method for deep neural networks. It's not that apparent right now, but know this. Know and understand gradient descent like the back of your hand, because it is going to be very useful in the future, okay? So I don't know why I'm showing that equation. That wasn't necessary. That was the equation for the sum of squared errors that we just talked about, sum of squared distances. Okay, so how are we going to calculate that gradient descent? Well, now let's actually do it, okay? So for our step gradient function, we'll start off with an initial gradient value for a b. So b is going to be 0, and so then m's gradient is going to be 0 as well. Okay, these are the starting points for our gradients, and gradient means slope. And so the gradient is going to act like a compass. It's going to always point downhill. So this is what I mean by, once we calculate that error, it's going to act as a compass for us. It's going to tell us where we should be going, what direction we should be going, how we should best redraw our line. So for okay, someone asked, why is the lowest point the best? The lowest point is the best because it is where our error is the smallest. And when our error is the smallest, that's when we have the line of best fit. When the error is the smallest, that B and M value, those two, when we plug into our slope equation, is going to give us the line of best fit. So that's why we're calculating the error, okay? So for I in range 0 to the length of points, okay, so what we're gonna do is we're going to iterate through every single point on our scatter plot. Okay, so every single data point that we have, we're going to collect it. Okay, so we're gonna say, okay, we'll start off with the first point, right? We'll start off with the first point, which gives us an X value and a Y value. X value and a Y value. So let me also write out a little comment for this. Starting points for our gradients, okay? Now we're going to get the direction with respect to B and M. Now, this is the last part, but it's a very, very important part. And this is where calculus comes into play, okay? So I'm gonna talk about how we're doing this. Okay, so let me talk about what we're about to do. So what we're going to do is, so for every single point that we have, we're going to calculate what's called the partial derivative. Okay, it's called the partial derivative with respect to B and with respect to M. Okay, and what that's going to do is it's going to give us a direction to go for both the B value and the M value, right? So remember, in this graph, we want a direction, right? We want to be going down the gradient, and so, right, so on this left-hand side, you see this gradient search. You see the M values and the B values are increasing in the direction that they should be, because gradient descent is essentially a search policy. It's a search policy. We're trying to find that minimum error value, okay? And what we're going to do to get that is we're going to compute the partial derivative with respect to B and M. Oh, and let me show you the equation for the partial derivative, okay? The partial derivative is going to be right here. Right, so this is what the partial derivative does. The partial derivative is, and we call, so we call it partial We call it partial because it's not telling us the whole story, right? We say it's partial because we're calculating for both B and M. There are two different things. And so it's going to give us the tangent line. So it's going to give us this line, as you see right here, right? See this line? That line is our direction, and we're going to use it to update our B and M values, okay? Okay? So that's what that is. And let me also show you the equation for the partial derivative, because we're about to write it out. So here's what the equation for the partial derivative with respect to M and B looks like, okay? There are two different equations, right? So let's talk about the one on top. So this little curvy thing that you see up here, that just signifies that this is a partial derivative. That's the math signifier that this is a partial derivative. Now, we talked about sigma notation, right? Because it's a summation of values, right? And that's what we're doing. We're summing the partial derivatives for all of our points, okay? For all of them to compute that gradient value, okay? And the partial derivative with respect to M and B is going to look like this. So let's write this out, okay? So the B gradient, so it's going to give us two values. So the B gradient is going to be plus equals, and then what was it? Let me look at the equation again. 2n, okay? 2 over n, so negative 2 over n, all right? And thanks, good vibes. And then we're going to, and then what was it? It was y minus, right? And these are equations. These are laws. They are beautiful laws that always stay the same. And they give us humans a way of understanding the direction that we want to move in. Okay, so B current. Okay, so all right, so then we'll do the same thing. And what was the second equation? It looked pretty much the same, minus this. It doesn't have this x, right? The second one doesn't have this x, right? So we'll say, but it does have this 2n. Okay. It does have this 2n, and then it does have let's see, it does have this x. It does have y minus m current times x plus b current. Okay. 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 So now we computed our partial derivatives, right? So let me one more time show you guys. It's giving us directions to go for both B and M. And remember, they're partial. It's not telling us the whole story. It's telling us what direction should we go for B and what direction should we go for M. And it's going to tell us the direction, remember, for a goal, to get to that bottom point where that error is the smallest, right here. Okay, so right here where my mouse is, that point is what we want to get to, and that's what the partial derivative is going to help us with. So once we've computed the partial derivatives, the sum of them with respect to B and M, now we're going to update our B and M values, right? So we're going to use that to update our B and M values. And guess what? This is our last step. This is our last step, using this partial derivative. Using our partial derivatives, right? Plural. There's two of them. So, and that's going to give us a new value for B and M, our updated B and M value. So we have our current value for B, whatever it is, that we fed into the step gradient function that keeps updating every time. And this is where our learning rate comes into play, okay? This is why our learning rate is so important, because it defines the rate at which we're updating our B and M values, right? So remember that 0.0001, right? And then also our M current minus learning rate times the M gradient. Okay, and then we'll return those values. And we're doing this every time, right? This new B and new M. It's not our final B and M. It's a step function. We're doing this every iteration, right? We're doing this for the number of iterations we had, 1,000. But it's going to return a new B and M value every time. And guess what, guys? That's it for our code. That was it. So let's go over what we've done. Okay, but let me check for errors, right? let me check for errors, and then I'm going to answer more questions because I really want to make sure you guys understand how this works. Okay, so let me demo this. So Python demo.py. Global name n is not defined. Okay. Oh, right. Guess what? I didn't define n. N is the number of points. Length of points. Okay. So let's go. Learning rate is not defined. Where? Where is learning rate not defined? Learning rate is not defined. Oh. Wait a second. Oh, yeah, right. Learning rate. Right. Okay, what else? What else is bad? I got an overflow for double scalars. Line 14. Total error. Y minus. Typo, learning rate, total error. Okay, so what's going on here? Okay, let's see this. So yeah, I mean, it printed out the final value. Okay, so it got our final value right here. And if we wanted to, let's see, hold on a second. If we wanted to, we get our back up here just in case. So, right, so let me blow this up like way up. And let me just separate it. So this is what our output's gonna look like. Right, so boom, just like that. That's how fast it traded, in milliseconds. Why? Because our data set was so small. Okay, its data set was so small. All right, so that's what happened. And after 1,000 iterations, we got the optimal B and M values. So right, we started off with B and M as 0, and we calculated the error for a random line that we drew, and it was huge. But eventually, after running gradient descent, we got the optimal B, the optimal M, and the lowest error point, which is at that smallest point in the bowl. And to do that, we use gradient descent with respect to B and M. Okay, so let me go over one last time every single thing that we've just done, just to really go over it, and then I'll do my last 5-minute Q&A, okay? So we started out by collecting our data set, right? Our data set was a collection of test scores and the amount of hours studied, right? The X, Y value pairs, the test scores and the amount of hours studied. A 2-variable data set. Then we define our hyperparameters for our linear regression. Our learning rate, which talks about how fast we should learn. Our initial B and M values for the slope equation, y equals mx plus b. The number of iterations, 1,000, because our data set is pretty small. And then we ran gradient descent. So what did gradient descent look like? Well, for every iteration, for 1,000 iterations, we computed the gradient with respect to both B and M. And we did that constantly until we got the optimal B and M value. That gives us that line of best fit. Now, how did we compute the gradient? To do that, we said, okay, we'll have a starting point of 0 for both of those gradients. Remember, gradient is just another word for slope. And then we said, okay, so for every single point in our scatter plot, for our data, we'll compute the partial derivative with respect to both B and M. And those two values are going to give us a direction, a sense of direction of where we want to go. How do we get to that lowest point in that bowl, right? That 3-dimensional graph, that lowest point. And we use the learning rates to determine how fast we want to update our B and M values. And we got the difference between the current value and what we had before, and we returned that. So for every point, and we did that for 1,000 iterations. Okay, and that's what it gave us, the output. And it looks like, visually, it looks like this, right? Right? It's like, it's kind of like Wheel of Fortune, right? It starts off fast and it gets slower and slower as it approaches convergence. The word we use when we have the optimal line of best fit, convergence. See, let me do it one more time. Just like that. Okay, so that was that. And now I'm going to screen share and do a last 5-minute Q&A. All right, stop screen sharing. Hi, everybody. Okay, let me bring you guys back on screen, do my last 5-minute Q&A. Ask me anything, yeah. How's it going, everybody? Any questions? I'm open to questions. Where did I use NumPy? It's at the very top. Suraj, what's the practical use of linear regression? Great question. Anytime we want to find the relationship between two different variables, and then in a more complex case there could be more, but we want to prove mathematically, right? Math is all about proving things in a way that is unfalsifiable, that no one can say, hey, that's not true. Well, I can prove it mathematically. So it's a way to show the relationship between two value pairs, right? So maybe housing prices and the time of year, right? So what is the real estate market going to look like? Or anytime that you intuitively think there was a relationship, you can prove it with linear regression. But really, I did this to show gradient descent. That optimization process that is very popular in deep learning, and we're going to use that in our deep neural networks in the rest of the course. Okay? Why are you biased towards Google? I mean, it's not really. Yeah, I mean, TensorFlow is awesome. It's not like Google's like, Suraj, I want you to talk about it. TensorFlow is the best deep learning library out there right now. That's why. And of course it would be, because Google knows what they're doing. They handle billions and billions of queries every day. They have to be able to do machine learning at scale. They've solved problems that no one else has even thought of solving. And all of those solutions are found in TensorFlow for machine learning. Please make an AI doctor. You can create a classifier to classify between different types of disorders that you see in an X-ray. That's going to augment doctors at first, but eventually replace them. How about fitting a quadratic curve instead of a linear line? We could do that as well. I'm going to provide the data set and the code. I can talk slower, sure. How to find the optimum learning rate? That's a great question. There's several methods of doing that, but that's great intuition. Sometimes we can use machine learning to find the optimal hyperparameter. So it's kind of like machine learning for machine learning. But we'll talk about that later. This is the first live section of the Udacity course. Teach us calculus. I'll do more of that in the future. I'm gonna keep doing calculus. Okay. 2 more questions and we're good to go. 2 more. How would you recommend me to start machine learning? Watch this series and watch my Learn Python for Data Science series. Watch my Intro to TensorFlow series. Watch my Machine Learning for Hackers series. Watch my videos. Why is your Udacity too expensive? I didn't decide the price, guys. I try to get it low. It's whatever. You got paid graders for that, okay? And grading is not cheap, human graders. But look, all the videos are gonna be released here on my channel. So, all right, so I'm here for you guys, okay? I'm trying to grow my brain, trying to grow myself, Suraj Rabal, okay? This is the end, okay? So that's it for the questions. And all right, so for now, I've got to shoot a fighting scene for my next video. What? Yeah, so thanks for watching. Mwah. Love you guys. I'll post the link in the comments right when I'm done, all right? Not in the video description. I'll post the GitHub link, and then the data set, everything is gonna go in the description within the hour. All right, bye. Okay.